P7, leptons. Now so far we know that some particles feel the strong force, and we call those hadrons, and some particles don't, and they're the ones we call leptons. So we're going to find out a bit more about what leptons are. So this is a summary of all the leptons. Actually you only need to know about some of them, but let's sort of give a brief summary. They're divided up into 3 generations. So one is the electron and its matching neutrino. So that's called the electron neutrino, and the symbol is a nu, which is a slightly curvy V, and it's got a subscript of E to denote that it belongs to the electron or goes with the electron. The second generation is, instead of an electron, we've got something called a muon, and that's like a very, very heavy electron. And in these little boxes you can see we've got some rest energies. So 0.5 MeV is the rest energy of an electron. A muon is 105 MeV, which is about 200 times greater. So it's a more massive electron. It's the electron's big brother. And there is a third generation, which is called a tau. So that's even more massive. And as you can see, it's 1.77 giga electron volts. So much, much heavier than even the muon. So as you go across the first, second, third generation, they get progressively more heavy. And each one has got a matching neutrino. So there's a muon neutrino and a tau neutrino. Now actually, for this course, you only need to know about the first 2 generations, because you need an awful lot of energy to make the third generation, so they're much rarer. But we're going to focus on generation 1 and 2. So what else have we got in this diagram? First of all, we've got charge. So as you can see, the electron has a charge of -1, and so does the muon, and so does the tau, as it happens. And the neutrinos have no charge, so they've got a 0 in the same position. In a lot of diagrams, you'll also see another number, which is a half for the leptons, and that's actually a number associated with something called spin, which is beyond A level, but so you might hear it mentioned. But it's another property of particles. At the top, we've got the rest energy, as we've already mentioned. The neutrino rest energy is not very well known. As you can see, this one just says less than 2.2 electron volts, less than 0.17 mega electron volts, and so on. So they're really, really tiny, even compared to an electron. But that's a summary. We've got 6 particles that are named leptons, 3 of which are electrons and its big brothers, and 3 of which are neutrinos and its slightly bigger brothers. And each one of those can have an antiparticle as well. So you can have anti-electrons, anti-muons, anti-neutrinos. So, leptons. We have some numbers that we associate with leptons. First of all, we need to know their charge. So in normal matter, leptons can have a charge of -1 or 0. And they can also have a lepton number. Now, that's basically just a way of counting them. It doesn't measure anything, it just measures whether they exist or not, really. So normal matter, leptons, have a lepton number of +1. So an electron, for example, is +1. So is a muon. So is a neutrino. Their antiparticles, the antileptons, have the opposite charge. So their charge will be +1 or 0. So +1 for an anti-electron or an anti-muon or an anti-tau, and still 0 for the anti-neutrinos. Their lepton numbers are -1, so they count as like negative particles. And that may seem a bit weird, but it's used to help us write down equations involving them. And just to remind you, all leptons are affected by the weak force, and the electromagnetic force if they are charged. So the electron, muon and tau are affected by the electromagnetic force, but not the neutrinos. But they're not affected by the strong force. Now, the reason we've got lepton numbers really is so we can check whether the lepton number is conserved and just work out whether some interactions are possible or not. So we know that lepton number is conserved, so is charge. So, for example, if we have electron capture, and remember that's when a proton in the nucleus captures one of the inner shell electrons in the atom. So we start off with a proton capturing an electron and combining to form a neutron. So if we count up the lepton numbers, so L for lepton, a proton isn't a lepton, so we give it a lepton number of 0. An electron is a lepton, and it's normal matter, so that's a +1. And a neutron isn't a lepton, so that's got a lepton number of 0. Now, as you can see already, the numbers on the two sides of this equation do not add up. We've got 1 on one side and 0 on the other. So we need another +1 on this side. Okay, so the solution is, if we need another lepton, we can put in a neutrino. Now, if we count up the charge on both sides, a proton has a charge of +1, and an electron has a charge of -1. That makes 0, +1, -1. On this side, we've got a neutron has a charge of 0, and a neutrino has a charge of 0, so that works. Okay, so we know it's a neutrino because it has no charge, and it is a lepton, and it's a normal matter lepton because its lepton number is +1. So that helps us solve the equation. Let's take another example. Beta decay is when a neutron turns into a proton and an electron. So it's sort of the opposite way around. So let's do the same again. Lepton number is 0 for a neutron, 0 for a proton, +1 for a normal matter electron. So we need a -1 here. So we need something with a lepton number of -1, so that has to be an anti-neutrino. Okay, -1 has to be an antiparticle. If we count up the charges, we've got no charge for a neutron, +1 for a proton, -1 for an electron, and 0 for a neutrino. Whether it's a normal one or an anti-neutrino, doesn't matter, still 0. So we've got 0 on this side equals +1, -1, +0, so that works as well. So as you can see, we can use the conservation laws to work out whether we've got, in this case, a neutrino or an antineutrino. Making things slightly more complicated, it turns out that the generations of leptons need to be tallied separately. So, for example, with muon decay, remember muons are the heavy electrons that decay up in the upper atmosphere and, of course, in particle accelerators. So for muon decay, we've got to remember that the lepton number is conserved in each generation of leptons. So we start off with a muon decaying into an electron. And if we count the lepton numbers, but we're going to be a bit more specific. So this is the electron generation lepton numbers, so generation 1. A muon isn't in the first generation, so although it's a lepton, it has an electron lepton number of 0. Okay, but the electron is in the first generation, the electron generation, so it has a lepton number of +1. So obviously that doesn't balance yet. If we add a neutrino, an antineutrino, that will help balance the books, because an antineutrino has a lepton number of -1 and it's in the right generation. So 0 equals 1 minus 1, that works. However, when we tally the lepton numbers for the second generation, so the mu leptons, we've got a muon here, so that's a lepton number, a mu lepton number of +1. An electron is not in that generation, so that's got a lepton number of 0 in the mu generation. So is the neutrino, so this doesn't balance yet. We need to add a +1. So this has got to be a second generation particle with a lepton number of +1. So we can do that by adding a muon neutrino. And it's got to be a normal particle, not an antiparticle, because this is a +1 and not a -1. Now, having done that, we need to also check that the first generation thing works as well. But of course, a muon neutrino is not in the first generation, so it's got a first generation lepton number of 0, so that still works. Okay, so if you've got mixed generations, you have to sort of count up the leptons separately for each generation. So this is the picture so far. We've split all matter into hadrons and leptons. So remember, the hadrons are particles that feel the strong force. Leptons are the ones that don't. Now within that, we've got, in the hadrons, we've got baryons and mesons. And the distinction between those so far is that all baryons decay into protons if left to their own devices, but mesons don't. They decay, but not into protons. And in the meson group, we've got two subgroups which we need to know something about, and they are pions and kaons. And all we know about those so far is that they come in 3 types. They can have positive charge, negative charge, or 0, and that's the same for both sets. And what we've done today is look at the leptons, the ones that don't feel the strong force, and we've got the electron, the muon, and the tau, although you don't need to know about the tau, and their matching neutrinos. Okay, so electron neutrino, muon neutrino, and the tau neutrino. So we'll come back to this picture in the following videos, but that's the story for now.